Welcome to the mathematics of juggling. In this video, we're going to learn about what a siteswap is. Siteswaps are the fundamental object that we'll be studying in the mathematics of juggling. Before I introduce the subject, I want to just acknowledge Ron Graham. Ron Graham is a former Mathematical Association of America president, a former president of the International Jugglers Association, and a popularizer of the mathematics of juggling. It's from him that I first learned about the subject and became very interested in it. This photo is credit of his wife, who has this on her webpage. In order to talk about the mathematics of juggling, we need a little bit of juggling. Here I am juggling the cascade, and what I want to do is I want to focus on the order in which the balls are caught. So here we go. They caught blue, red, green, blue, red, green, blue, red, green, blue, red, green. What we'll do is we'll mark on our screen here the colors of the balls in which they're caught. Blue, red, green, and so forth. Another popular juggling pattern is what's known as the shower. In the shower, the balls go in a circle, and it's a little more difficult for me to call out the colors because it goes a little bit faster. Here we go. Blue, blue, green, red, blue, green, red, blue, green, red, blue. Oof, that's hard to do. But it goes blue, red, blue, green, red, blue, green, red, blue, green, red, and so forth. Finally, our last pattern we don't have a name for until we get the notion of a siteswap. Let me show it to you and call out the colors. Here we go. Blue, red, green, yellow. Okay, so this isn't really easy to call out the colors. Let's slow it down just a bit. Here we go. Blue, blue, red, so two blues and a red, green, green, blue, two greens and a blue, red, red, green, two reds and a green. Let's mark that down. So here we have blue, red, green, blue, red, blue, green, blue, red, green. It's difficult even with colors right in front of me to say out what's going on. What we've done is we've taken the concrete action of juggling and replaced it with an abstract representation on our screen here with just these colored balls. We're going to make things more and more abstract as we go, not abstract in the sense of way out there, but just abstract in you wouldn't recognize what we're looking at as representing juggling. I'm going to reduce the size of those balls to what we call vertices here. A vertex is a dot on a piece of paper. That's the singular vertex. Vertices is the plural. It's part of a mathematical graph. And in a mathematical graph, we also have edges. An edge is a line between vertices. I'm going to connect two vertices with an edge if they're consecutive vertices of the same color. So here we have the first two blue vertices will color together with an edge. The first two red will color with an edge. The first two green will connect with an edge. And then we continue to do that throughout. We'll do the same thing in the next graph. Notice that the first two blues are far apart and the first two greens are very close together. And then we continue to draw those so that consecutive vertices of the same color are connected. In the last one, we have a somewhat long blue one and a somewhat long red one, and then a short green one, and then we continue on further. We can continue in our path of abstraction by writing beneath any vertex a number that corresponds to how many vertices it is before that edge lands. What do we mean by that? Well, in the first graph, notice that the first blue is 3 spaces away from the second blue. The first red is 3 spaces away from the second red, and so on. In the second graph, corresponding to the shower, the second blue is 5 spaces after the first blue. The second green is 1 space after the first green. And so this alternates 5 red, or 5, 1, 5, 1, 5, 1, and so forth. Let's look at the last one. Pause the video and see if you can figure out what numbers will be associated with this. The second blue is 4 from the first blue, the second red is 4 from the first one, and the second green is 1 from the first green. What we'll do when we talk to our juggler friends is we'll just tell them the short sequence of numbers that keeps getting repeated. The cascade is known as 3, the shower is known as 5, 1, and this new pattern is known as 4, 4, 1. We're going to extend our abstraction by acknowledging the fact that the colors are no longer relevant now that we have the numbers. Let's make the ones in the bottom one black. Don't worry about the other graphs. Now we want to look at the graph and see what's important to make this juggleable. We're going to blow up a later part in the graph, And we'll observe that in the first beat depicted, we have one edge on the left coming in and one edge on the right going out. Left coming in means a ball landing, right going out means that ball is being thrown. We have that throughout. What we want to do is we want to avoid two edges coming in at the same time. Because we have two edges coming in at the same time, that means the two balls are being caught at the same time. Let's look at some other things and look at the fundamental question, when can a list of numbers represent a juggling pattern? Here we have 7562, 7562. Will this represent a juggling pattern, what we'll call a Siteswap later? Well, we'll draw an edge, from the first vertex, out 7 vertices later. The second vertex, we draw an edge from there, so it lands 5 vertices later, then 6, then 2. So far, so good. We don't have two edges landing at the same vertex. If we continue that, 7562, 7562, 7, notice that there is no vertex that has two edges coming in at the same time. This appears to be and is a Siteswap. Let's try another sequence, 4, 9, 8, 7. The first 4 will be 4 beats later. The 9 will be 9 beats later, way, way out there. The 8 will be 8 beats later, way, way out there as well. And look what just happened. Those two balls are landing at the same time. That cannot happen. So 4, 9, 8, 7 is not a Siteswap. In order to determine when a list of numbers is a Siteswap, we need to look more closely at those landing times. I'll take our pattern of 7562 and investigate it further. The time at which we catch and throw a ball is what's known as a beat. It's a beat because it's sort of rhythmic. Da, 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 da. The height is the length of time a ball is in the air. Now I've highlighted one of our edges, the red edge from the second throw of height 7 out to whatever throw that is that's going to be next of height 2. That throw of height 7 takes place at beat number 4. It's in the air for 7 beats, so it's going to land at beat 11, simply the sum of 4 and 7, which will be 11. In general, the landing times are the sum of when the ball is thrown and how long it's in the air. Notice that this list of numbers, 7, 6, 8, 5, 11, and so on, doesn't have any repetition. Now, I chose this particular Siteswap as an example because it uses all different throw heights, 7, 5, 6, and 2. All of the landing times corresponding to throws of height 7, I'm going to color yellow. Those that correspond to a throw of height 5, I color orange, and so on. The ones corresponding to a throw of height 7 land at beats 7, 11, 15, next would be 19, and so forth. Observe that they're 4 spaces apart. The reason they're 4 spaces apart is because we have 4 numbers in our list, 7, 5, 6, 2. Let's collect these numbers. The throws of height 7 land at beats 7, 11, 15, 19, and so on. The throws of height 5 land at beats 6, 10, 14, and so on. And if we look at these numbers as a collection, for example, look at the landing times corresponding to throws of height 6, 8, 12, 16, 20, and so on. Those you might recognize as multiples of 4. They're all divisible by 4. When we say something is divisible by 4, that means that when we try to divide it by 4, we get a remainder of 0. Landing times corresponding to throws of height 2 are 5, 9, 13, 17, and so forth. If we divide each of those by 4, we get a remainder of 1. There's this consistency. The landing time for throws of height 5 all have a remainder of 2 when we divide by 4, and the landing times for throws of height 7 all have a remainder of 3. What's really important to here, and this is again a function of the fact that we are looking at a Siteswap with all different numbers, but landing times for a particular throw all have the same remainder when we divide by 4. It's not the particular throw, but its position in the list of numbers, the first number, the second number, third, or fourth. In order to go through and discuss the actual mathematical way of checking to see if a list of numbers is a Siteswap, we need to introduce a new concept, which is known as modular arithmetic. When I divide a number a by n, the remainder we get when we perform that operation is written as a mod n. When I divide 21 by 8, I get a remainder of 5, so I'll write 21 mod 8 is 5. When I divide 97 by 20, I get a remainder of 17. 97 mod 20 will be 17. And 2,294 divided by 37 is 62 with a remainder of 0. So 2294 mod 37 is 0. Now we're ready to formally state what it means to be a siteswap. If we have a list of numbers A0, A1 up to A sub n minus 1, it's a period n siteswap. The period means that's how often it repeats. It's of period n because there are n numbers in our list. If all of those landing times, when we reduce them mod n, that is, when we divide by n and look at the remainder, if all of those landing times are different, then it's a siteswap. What's really kind of important to keep in mind here is that if you take any n consecutive throws, the landing times will leave different remainders when dividing by n. Let's try this method with some of the ones that we're familiar with. 7, 5, 6, 2. Those are 4 throws. We're going to look at the first 4 beats, 0, 1, 2, and 3. When I add 0 and 7, 1 and 6, 2 and 6, and 3 and 2, we get 7, 6, 8, and 5. When we divide each of those by 4, we get remainders of 3, 2, 0, and 1. We're dividing by 4 because there are 4 numbers in our list. If we look at the failed one, 4, 9, 8, 7, when we add 0 and 4, 1 and 9, 2 and 8, 3 and 7, we get 4, 10, 10, and 10, already looking bad. When we divide each of those by 4, we get remainders of 0, 2, 2, and 2. Those have repetition, and so it's not a siteswap. We learned about the new pattern 4, 4, 1. That's only 3 numbers, so we'll look at the sums mod 3. 0 plus 4, 1 plus 4, and 2 plus 1 give us 4, 5, and 3. When we divide each of those by 3, we get remainders of 2, 1, 2, and 0. All different, so it's a siteswap. Let's introduce a new list of numbers and let you check on your own. How about 5, 2, 4, 5? Is it a siteswap? We're going to look at those sums mod 4. So give it a try and pause the video. When we look at the sums, we get sums of 5, 3, 6, and 8. When you divide 5, 3, 6, and 8 by 4, we get remainders of 1, 3, 2, and 0. Dividing 3 by 4 is kind of funny. 4 goes into 3 0 times, but we still have a remainder of 3. That's a siteswap because they're all different. I want to introduce a new way of looking at this finding the number mod n. In order to do that, we need to review what we mean by division, or another interpretation of division. One way to interpret division is its repeated subtraction. So think about this. Suppose you have a favorite cereal. It costs $3 and you have $20 to spend. How many boxes can you buy? The simple way to do this would be to do division. 20 divided by 3 is 6, and I have $2 left over, so I can buy 6 boxes of cereal. If we're going to be lazy, what we could do is we could go grab 1 box of cereal, run to the counter, pay for it with our $20, get change. If our change is $3 or more, we can go back and buy another box, which we can with $17. We go back and buy another box, pay for it, we'd get $14 back, and so forth. How many boxes can we buy? Well, we can buy 6. At the very end, we end up getting change of $2, which we can't use to buy a new box of cereal. Notice that the remainder is 2. That's how much money we have left at the end, and that's going to correspond to the mod. We'll do an example to illustrate why this is important. Well, we'll learn why it's important in another video, but we'll do an example to illustrate how to do this. In order to do that, I wanted to just introduce a nice little fact. If you have a siteswap, a cyclic shift of that siteswap will also be a siteswap. We've been picking on 7562, so let's do that some more. 7562 is a siteswap. If you shift that 1 over 5627, that's also a siteswap, as is 6275 and 2756. We're going to check that 2756 is a siteswap using my repeated subtraction method. What we do is we form the sum as we did before. It's a period 4 siteswap. We're going to use the first 4 numbers, 0, 1, 2, and 3, add those to 2, 7, 5, 6 respectively to get the sums of 2, 8, 7, and 9. Rather than divide these by 4 and look at the remainders, we're just going to subtract 4 whenever we can. I'm going to draw a dotted line. In another video, we'll learn what's special about the numbers below that dotted line. When I subtract 4 from 8, 7, and 9, we'll get 4, 3, and 5. If any of these numbers are 4 or larger, we'll subtract 4 from them. So we'll subtract 4 from 4 and 5 and get 0 and 1. Now the numbers at the bottom of each of those columns are less than 4. They are 2, 0, 3, and 1, all different. Those are the remainders we would get when we divide by 4. And so that is a siteswap. One last little exercise for you to try. In order to do that, I want to introduce just a little bit more. When we use numbers larger than 9, we'll replace them with letters. A will correspond to 10, B to 11, C to 12, and so forth. The reason we do that is because if I see a 2 and a 4 in my Siteswap, I want to think of that as a 2 and a 4, not as a possible number 24. 24 would be something altogether different, using a letter. As an exercise, determine if D19151 is a Siteswap. We would set it up like so. Now we would add the beats and the throw heights to get 13, 2, 11, 4, 9, and 6. This is a period 6 Siteswap, potentially. So we'll subtract 6 from any number that's 6 or larger. We can do that from 13, 11, 9, and 6. From 13, we get 7. We can still subtract 6 from 7. We get 1. If we look at the bottom numbers in each column, we get 1, 2, 5, 4, 3, 0, all different, and so it is a Siteswap. I really like this one, and this is what it looks like. You'll notice it's kind of like a 3-stacked shower. You've got 3 different showers taking place here. As a little piece of trivia, 9151 is also a Siteswap. Check it out on your own. Where are we going to go from here? Well, I've got 2 videos that will be coming up from following this one. First of all, if you have a Siteswap, how do you know how many balls are needed to juggle it? We'll give a couple of different answers for that. In general, if you have a list that's a Siteswap, how can we figure out how many balls there are? I'll also do another video in which I just talk about the mathematics or the juggling aspect of these numbers. What is the significance of each throw height? If you like the little juggling guy that you've seen here, you can play around with him. That's available at jugglinglab.org. It's a really simple interface, a nice little program to play around with.